in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello learners, welcome to yet another class of mathematics. We studied before some part of matrix chapter and now here we are continuing further. We study here multiplication of two matrices. Now this is very crucial part of this particular chapter. Now here when you talk about multiplication of two matrices, here we are multiplying two matrices. In the previous case when we were talking about multiplication of matrix by scalar, one scalar we were taking and we were multiplying to the matrix. But here what is happening? Two matrices we are multiplying. Now over here this is very moody multiplication. Now why I am saying it is very moody multiplication? Because here see, if there is mood of getting multiplied, in the sense what I am saying, if the given matrices are conformable, what does it mean? Here see, when you say, here see, two matrices A and B are conformable for multiplication when the number of columns of first matrix, right now I am considering as matrix A, is equal to the number of rows of the second matrix. Right now we are considering it as matrix B. Now look at the example, look at the general format here. See, matrix A, I have the order as m cross n. Number of column of first matrix, that is n, is equal to number of rows of the second matrix, that is here n. Look at this, n, right? So since both are same, the matrix multiplication is possible. This is like a litmus paper test. If you want to multiply two matrices, first of all I need to check whether given two matrices are conformable or not. If they are not conformable, matrix multiplication is not possible. But if they are conformable, yes, you can proceed further to multiply given two matrices. Now let us see here. Now over here, as I said, number of column of the first matrix is equal to number of row of the second matrix. Now both of them are equal. Now whatever is left over in the sense what? Number of rows of the first matrix and number of column of the second matrix. These two left over rows and column will give me the new order of the product. Okay, so over here see what is order of this A into B, that is m cross n, the leftover part of matrix A and leftover part of matrix B. You can see m cross s, right? Now over here the product I considered A into B. But now suppose if I consider B into A, it is not possible. Why B into A is not possible? Because B I need to take first. So you can see here n cross s and here I have m cross n. Now number of column of the first matrix is not equal to number of rows of the second matrix. So it is not conformable and hence the matrix multiplication is not possible. Okay, let us talk about example. Now look at this example. Now here I have matrix A of order 3 by 2. I have matrix B of order 2 by 2. Look at this, number of column of the first matrix is equal to number of rows of the second matrix. Yes, 2, 2, right? Equal. Now what is leftover part? 3 and 2. So look at this, the leftover part will become new order. Okay, so now over here what I have 3 cross 2 is the order of my new product that is A cross B. Look at this here, 3 cross 2. So it will have 3 rows and 2 columns. So the structure of my matrix, structure of my output will be this. Okay, now let us look in another way. Another way in the sense, see, I want to do B into A. Is it possible? Look, number of row of the first matrix, that is 2, number of column of the first matrix, that is 2. Is it equal to number of row of the second matrix? 3? No. 2 is not equal to 3, right? So the main thing what we are talking about, the number of column of the first matrix is not equal to number of row of the second matrix, and hence B into A is not possible. Why? Because these two matrices are not conformable for matrix multiplication. So this test is like a litmus paper test to check whether the given particular multiplication is possible or not. Okay, now here let us look at this, matrix multiplication step by step. This is very important and very crucial concept. Many of you misunderstand this, so please pay attention when I am explaining. Now look at this. I want entry A11. So I am talking about entry A11. Now look at this. So here see, I am talking about first row, first column. Now here see what I will do. A into U plus B into W plus C into Y. Look at this here, that I will take and I will add. So this A into U plus B into W plus C into Y. Look at this. This is my A11 entry. Let us look at the next entry. Next entry is what? A12. Now this suffix numbers will give you the address. Now look at this here, I am talking about, see I am focusing on first row and second column. See, first row remains steady. So first row, second column. See what I am getting, AV plus BX plus CZ. Look at this, I am getting second entry of first row. Now if you look at it carefully, see I am talking about first row only. So you can see the first row I am keeping stable, steady. What I am shifting over here is only the second column. Okay, fine. Now I finished getting entry of my first row. Now it's time to get entries of my second row. So since I am addressing here A21, so 2 signifies second row. So over here, see second row I am highlighting here and first column I am highlighting. Why? Because 2, 1. So here D into U plus E into W plus F into Y. Look at this. Okay, so this is what position? A21 position. Perfect. Now let me proceed further for the fourth entry. Fourth entry is what? A22. So again, as I told you, this is the mapping for your entry. Now over here, see, I am talking about second row only. So second row remains steady. So now I supposed to shift where? For the second column. Why? Because it is 2, 2. So second column. So I will be focusing on second row, second column. So D, V plus EX plus FZ. So this is how I get my fourth entry as well. Okay, now over here see how I get to know the structure of the matrix. Now look at this here. This matrix is of what order? This matrix is of 2 by 3 order, right? Now this matrix is of what order? 3 by 2 order. So now here see 2 by 3 3 by 2. So 3, 3 same. So what final output I am getting? What are the leftover entries? Here 2 cross 2. So I am getting here 2 number of rows and 2 number of columns. Okay. So you can see here the final product what I am getting is, here see, these are the 2 rows, these are the 2 columns. So over here I am getting, here see, 2 rows, 2 columns. So the order of the matrix is 2 by 2, or you can say the matrix is a square matrix of order 2. Now let us talk in terms of numbers. Now over here see, first of all I must check whether the given matrices are conformable or not. What does it mean? Whether matrix multiplication is possible or not. How to find out? Let us look at the order of these two matrices. So over here, see what is order of this matrix? It is 2 by 3, perfectly fine. What is order of this matrix? It is 3 by 2. Okay, so number of columns of the first matrix is equal to number of rows of the second matrix. So now since 3 gets cancelled, what is left? 2 and 2. So that's how I get over here as 2 cross 2, and here see we are getting 4 entries over here. So 2 rows, 2 columns. Okay, so look at this now. To get my first entry A11, what I did? Here see, the first row, first column, I need to multiply and add. Look at this, A1 plus B2 plus C3. Look at this. Okay, I got the first entry. I am going to the first row, second entry. Since I am talking about first row, second entry, first row remains stable. So over here, first row, second column. Okay, so A into 4, so plus 5B plus 6C. You can see here I am getting second entry of first row. Let's talk about, here see, second row, first entry of second row. So I am talking about second row, first column. So similar way I need to multiply and add. So I say 1D plus 2E plus 3F. Look at this. Same way I am getting over here, second row, second column. So it is 4D, right? Then you get 5E, then you are getting 6F, and you are adding it all. Okay, so this is how you get the entries. Let us look at the numbers here. Look at this, A into B. By the way, both are square matrix. So I can say both of them are conformable for multiplication. Hence, matrix multiplication is possible. So look at this, the output again will be square matrix. So very crucial statement what I am making. If you take two matrices of order 3, you will get final output as matrix of order 3. If you get both matrices of order 2, you will get final output as matrix of order 2 only. Look at this now, first row, first column. So 2 into 5, sorry 1 into 5, look at this, plus 2 into 7, check. Now when I multiply 5 plus 14, I am getting as 19, perfect. Let's proceed further. Here see, I am talking about first row, second column. So 1 into 6, here see I am getting 1 into 6, plus 1 into 8, 2 into 8, look at this, I am getting 2 into 8. Okay, so now here when I add 6 plus 16, I am getting it as 22. Same way I am talking about second row, first column. So 3 5s are 15, okay, plus I am getting over here, see 4 into 7. So when I add this 2, I am getting it as 43. Same way over here. Again second row, second column, so 3 into 6, Here I am getting 4 into 8, I am getting here, when I add these two answers, I am getting it as 50. Okay, so this is how, if you have more and more practice, you can make these calculations very quickly. See, these are the practice problems which are given to you all. There are 5 pair of matrices which are given, and the statement tells you find AB and BA for the following pair of matrices if possible. Now, why it is given if possible? Because whenever you want to proceed with matrix multiplication, first thing what you need to do, that is you need to check whether the given matrices are conformable or not, whether given matrix multiplication is possible or not. That's the first thing. And when you see that, whatever order of the matrix you get, that will help you to build your output matrix. Okay, so that's why finding out whether the given two matrices are conformable or not is very important step. Okay, so let us look at the next, that is properties of matrix multiplication. So this kind of properties first we studied in terms of matrix addition. Now look at this commutative property. Now this commutative property is not true in terms of your matrix multiplication, but in terms of matrix addition the commutative property is true. Now over here see, it is sometimes you can get A into B is equal to B into A when you have a square symmetric matrix. Now what do you mean by symmetric matrix? We will study further. Okay, now for now you just remember it is commutative in the case when you have square matrices of symmetric in nature. Okay, next, second one, associative property. Now when you talk about associative property in terms of multiplication, you can see A into B, when you multiply into C, whatever product you get as matrix, that matrix is equal to this kind of representation. So if you take B into C first and then you multiply A, whatever output you get, the output will be the same. And again, as I say, the associative property holds true here. Third case. Now third case, you have see left distributive property, right distributive property. What does it mean? Now over here see, when I say left distributive property, in the sense here see the matrix A which is at left side, okay, and it is getting multiplied in the bracket. Fine. So when it is getting multiplied in the bracket, what is happening over here? See, it is getting distributed over addition. So you are getting see AB plus AC. What is happening here? It is getting distributed over addition from left. So that's why it is called as left distributive property. Let's go to right distributive property. Again, the same kind of explanation I would like to give you here. This matrix C is multiplied in this bracket from right, and it is getting distributed from right side. So that's why you are getting here CAC. You are not getting CA, you are getting AC. From right it is getting distributed. So AC plus BC. Okay, you cannot write CA. It is AC only. You cannot write CB. It is BC only. Why? Because commutative property does not hold good over here. Next is existence of multiplicative identity. Now here see, when I talk about existence of multiplicative identity, basically when you multiply any matrix with identity matrix, you get back the original matrix. You can see over here A into I is equal to A. You are getting original matrix back. Same way here I into A, you are getting original matrix back. So I, what is this I? I is identity matrix, what we consider over here. So I is called multiplicative identity. In terms of matrix addition, what was your additive identity? That is null matrix was your additive identity. Okay, now over here this sixth one. Now over here when you talk about this, here see you can see, here I am talking about here A raised to m into B raised to n. If you have this kind of matrix with power m and n, what you can write? You can write it as A raised to m plus n. This is one of the law of exponent. Okay. Similar way you can write it as here A raised to n into B raised to m. What you call for it? You call for it as positive integral power of square matrix. What you call for it? Positive integral power of square matrix. So over here see, look at this. A square I can write it as A into A. Look at the power here. 1 plus 1. You are getting 2. Look at this. A raised to 3. You can write it as A square into A. So it is 2 plus 1. You are getting power as 3. And it goes on. Let's discuss problems. So when you talk about this problem here, look at this. If A equal to, you have square matrix of order 3, show that A square minus 4A is scalar matrix. What we studied about scalar matrix? Scalar matrix is a diagonal matrix where along the diagonal you have one particular constant, same constant. Okay. So you need to get A square minus 4A as scalar matrix. Look at this. For what I'll do, first I will find A square separately. Just now we studied how to multiply two matrices. So over here look at this. I stated first itself, when you multiply two square matrix, they are always conformable for multiplication. So you don't have to waste time over there to check whether they are conformable. Okay. So here you see 3 by 3, 3 by 3. So the final output is 3 by 3. And as I showed you different steps of matrix multiplication, same way you need to get your answer done. See, first row, first column will give you first entry. Same way, first row, second column will give you second entry over here. First row, third column will give you third entry over here. So I finished with the first row. Now let us go to the second row. So second row, first column will give me this entry. Second row, second column will give me this entry. Second row, third column will give me this entry, and so on. So when I add these all elements, I will be getting answers as this. Okay. So I got A square as this 4A. So constant 4 is multiplied to this matrix A. So it's a scalar multiplication, right? So what is happening? 4 is multiplied to each and every entry over here, and you get the final output as this matrix. So these two now I will put in my equation. You can see this is my LHS, that is A square minus 4A. I am substituting A square here. I am substituting 4A from here. Look at this. And when again here it's a negative sign here. So I need to find difference of two matrices. So when I find difference of these two matrices, I will get here, see, 9 minus 4. 9 minus 4 is 5. 8 minus 8, 0. 8 minus 8, 0. So you will get answer such a way that the final output what you have over here, that will be a scalar matrix with scalar as 5 along with the diagonal. See here it is show that. Show that means it has to be scalar matrix. You are no one to say it is not scalar matrix. If you are not getting answer, that means somewhere you must have made mistake. Okay, so you need to go back and correct yourself. Let's go to the second problem. Let's hear. Second problem. If A equals this matrix, show that A square is null matrix. Again, show that. What does it mean? That the statement is true. So anyhow, you need to give proof that the statement is true. Okay, so now over here see A square. So I will be finding A square. So A into A, I have square matrix over here. So when two square matrix you multiply, what you get? The final output you get it as again square matrix. So you don't have to check whether the given two matrices are conformable or not. So here see when you multiply, see first row, first column will give you this entry, first row, second column will give you this second entry, same way second row, first column will give you this entry, second row, second column will give you this entry, and the output you are getting effectively, that is 0, 0, 0, 0, and this is nothing but null matrix of order 2. Now why you are getting order 2? Because here see you are multiplying two square matrices. Next problem here. If A equals a matrix of order 2 you have here, show that A square minus 5A plus 7I equal to 0. Show that. Again the statement is true. So the final output what you must get over here as null matrix. Okay. So A, you have A with you, again 5A. Whatever A you have, with that you can get your 5A, but here see you have 7I. Do you have I matrix here? No, I need to consider I matrix. How I will consider? Look at this. I have matrix of order 2. So I will take identity matrix of order 2 only. And to that I will multiply 7. So what I will get? I will get a scalar matrix with diagonal entries as 7. You can see here 7I equal to, you can see 7 gets multiplied to the identity matrix of order 2 and you are getting it as this. Perfect. So A square you are getting in this way. Again see you need to do this matrix multiplication using all procedures correctly. Then you get 5A, it's a scalar multiplication, you get this matrix. So what have to do? This, this and this output what I got, I will be substituting in my LHS. See the writing part is very important. So what is my LHS? LHS is this, A square minus 5A plus 7I. So what I will do, I will just substitute all the matrices and I will, here see, it's a subtraction addition. So 8 minus 8 plus 7, see, 8 minus 8 plus 7 will give you 0. Perfect. Let's go to the second entry. So 5 minus 5 plus 0. 5 minus 5 plus 0. Are you getting 0? Perfect. Next, it is minus 5 minus of minus 5 plus 0. You can get here, see, effectively 0, and the similar way you get your fourth entry as well. Perfect. So are you getting here the matrix which is having all entries as 0? What kind of matrix it is? It is your null matrix of order 2. Why? Because order 2, because you have here A as square matrix of order 2. Now suppose if I have here square matrix of order 3. So what kind of identity matrix I will take? I will take here identity matrix of order 3. And 7 will get multiplied to it to get your scalar matrix of order 3 with the diagonal element as 7, 7 and 7. Perfect. So let's proceed further for the next. Now here, the next kind of problem. Find x, y and z if you get here, see, this kind of equation. Now here BODMAS rule comes into the picture. What your BODMAS rule says, you need to solve brackets first, right? So you can see there are two matrices here in brackets. So what I will do first, I will solve those matrices. So I am getting 2 here, which is multiplied to this matrix. So scalar multiplication, so 2 will get multiplied to every entry, and here see I am getting it as, see I am getting here as, here see, it is 2 into 2 4, then 2 into 1 is 2, then 2 into minus 1 is minus 2. So I get this entry, this matrix here, minus of this matrix. So I will find a subtraction of two matrices. So 4 minus 3, I am getting it as 1, look. 2 minus 2, I am getting it as 0. Minus 2 minus of minus 3, I am getting it as 1. So the output of these two is this, which is there in curly bracket. Okay, so this matrix I need to multiply with this. Now actually here see I need to multiply two matrices. Now over here see, are they conformable? Let us check. Look here, this order is what? It is 3 by 2. What order of this matrix you have? 2 by 1. 3 by 2, 2 by 1. So 2, 2 same. So what is left over? 3 and 1. So 3 into 1 is the order of your final product. Okay. So you are getting here, see when you use here, see first row, first column. So you are getting 1 into 1 and plus 0 into 2. So you are getting 1. Again here see I finished with the first. So I am going to the second row, first column. I am getting this value. Then third row, first column. I am getting this value. Okay. So this is equal to this. So at the beginning when we studied equality of two matrices, I said both matrices supposed to have same order. That's the first condition. So are they having same order? Yes, 3 by 1, 3 by 1, right? And here see, second condition was what? Second condition says the corresponding entry is supposed to be equal. So you can see with that I say x equal to 1, y equal to minus 1 and z equal to 4. So what is the value of x? 1. What is the value of y? Minus 1. And what is the value of z? 4. So these are the practice problems what I have for you people. You can pause this video and take down these all problems and practice it for more perfection. Now here I gave answers also if you people want to confirm your answers. Okay, so here see whatever problems I have discussed, similar problems, similar situations I have given you all so that you can practice them and get your answer done. Next we talk about transpose of a matrix. Now here what do you mean by transpose of a matrix? It is the matrix obtained by interchanging rows into columns of the given matrix. It is denoted by A dash or AT. It is very important. It is denoted by what? It is denoted by A dash or AT. Okay. So over here, see how you write A equals, this is your original matrix. I am finding the transpose of it. So what will happen? The number of rows will become number of columns and number of columns will become number of rows. So over here see m cross n will now change to n cross m. This is very, very important. Okay, and here see I comma, here see you have ij. Now here what is happening when you take transpose? In ith place you will have j and in jth place you will have I. Okay, so it is very important. So what is transpose? The transpose of matrix is the matrix what you get by interchanging rows into columns. Okay. Next here, example, look at this. I have matrix of order 2 by 3. Look at this first row now will change to first column. See, ABC, now it became what? ABC as first column. So what is happening? Row I am changing as column C. Second row again will become my second column. So what is happening? 2 into 3, see, I am having here as 3 into 2. Okay, so the order also interchanged. So here the order of transpose is 3 by 2. What is order of your original matrix? It is 2 by 3. Let's go for the second example. Here you have matrix A equals, here see, a row matrix. When you talk about row matrix, the order is what? 1 is to 3. Sorry, 1 cross 3. So when you say this row I am interchanging as column, what I get? My output I get it as column matrix. So over here see the order changes. So it is 3 into 1. Okay, 3 into 1, see I can have as many columns, rows I can, but the column supposed to be 1. Okay, so this is row matrix. When I take transpose, I get it as column matrix. Now we need to discuss some properties of transpose of a matrix. Okay, so these are very important properties what you need to study. So you can see A dash, when you take the transpose of it, if you remember your set theory what you learned in your 11th standard, you remember you were saying complement of complement is the same set. Same way I say over here, the transpose of transpose, what I said, the transpose of transpose is your original matrix A. Second one, here see, if the constant is multiplied to the matrix and if you take the transpose of it, effectively that K constant you can take out as common and you can say A transpose. Okay, so K is what? Your constant. Now here see, when you add two matrices, okay, and if you take the transpose of it, it will be equal to the transpose of first matrix plus the transpose of second matrix. Now this is very important. This fourth property is very important property. You can say this as like reverse property. You can see A into B the whole dash. A into B the whole transpose, when I find, okay, whatever output I get, the output will be equal to B transpose into A transpose. Not A transpose into B transpose. It is what? B transpose into A transpose. So A into B the whole transpose is equal to B transpose into A transpose. So this is the extension of this fourth property. You can see here A into B into C. So the product of three matrices when you take, and when you take the transpose of it, it will be equal to C transpose into B transpose into, okay, so these two properties are very crucial, and this fifth property is just an extension of your fourth property, and these are very important questions for the exam point of view. Let us talk about problems. Now over here see, I have three matrices with me, matrix A, matrix B, matrix C. Now over here see, I need to verify this all properties. See, I said verify, I never said show that. If I say show that, then all these properties supposed to satisfy. I said verify. So it may satisfy, it may not satisfy, okay. So verify the following properties. Now here see, all these properties we discussed before. Now here see, A into B the whole transpose equal to B transpose into A transpose. I am talking about the first one, look at this. See, this is my LHS, this is my RHS, okay. Now to get my LHS, see, I have what in the bracket, A into B, perfect. So now I am multiplying two square matrices. So when I multiply square matrices, the final output will be again square matrix. So I don't have to check for the conformability over here. So when I multiply two matrices using proper protocol, I am getting the output as this. Look here, see, I gave all the steps properly written over here. You can pause this video and find out whether you people are getting the same answer or not. Okay, and then afterwards we start with LHS. Look at this, LHS is what? A into B the whole transpose. Okay, A into B, I got this matrix, I am substituting here. So the transpose of this matrix, what I am getting? The rows I am changing as columns. So minus 11, 10 comes here. 5 minus 16 will come over here. Okay, so this is my LHS. I am talking about RHS now. So RHS is what? B dash, or you can say B transpose into A transpose. So I take my matrix B here. I take my matrix A here, and I will take transpose of each matrix separately. Okay, so when I do so, see, you can see here matrix of, here see, the transpose of B. Here see, I am getting 1, 4, 1, 4. 4 minus 2, 4 minus 2. So this is the transpose of matrix B. Now, matrix A the whole transpose. So 1 minus 3, here see, you can say 1 minus 3, minus 3, 2. So minus 3, 2. So now these two matrices I need to multiply. They are square matrices. So what I am getting answer as, you can see here, as this after using proper protocol. Okay. So here I am getting this matrix here as my RHS, this matrix as my LHS. Are they equal? Just observe, yes. So I am getting LHS equal to RHS. So hence I said A into B the whole transpose is equal to B transpose into A transpose. I have got, it is verified. Okay. Let's go to the second one. I am talking about the second one. Look at this. Now, when you get problems where two sub-questions are given together, see that whatever things you got from your first section, you use it effectively in the second section. This is how we did it over here. See, A into B, we found it in the first section, so I took it here. See, now what I will be doing, see, in the bracket I have A into B into C. So A into B I got, that I have written over here. Into C, the matrix C I have taken here. So I will be multiplying these two matrices. So I am getting here, see, the output as this. Okay. Now this I supposed to take and I need to find the transpose of it. Look, so it is 52, 9, 52, 9. The row will become column. This second row will become second column. Is it happening same way? Yes. My LHS, I am getting it as this matrix. Let us talk about RHS. Now when I talk about RHS, see, C transpose we already found in the previous case. Let us take that. A transpose again we found. B transpose also we got. So all these three things we supposed to get, okay, from our first sub question. And once I get it, here see, I multiply it and I am getting in this way. Here see, this is my matrix C transpose. I multiply here C, B transpose and A transpose. I get here as the product of A transpose into B transpose into A transpose, and I am getting here see, C transpose into B transpose into C transpose. Here see, you are getting this, here see, what matrix I have given in the red here, see this matrix and this matrix, I mean to say my LHS and my RHS, is it same? Yes, it is same. So what I am getting over here, I also verified my second question, that is A into B into C, the whole transpose is equal to C transpose into B transpose into A transpose. Okay. So here, see now these three things I want you people to do as practice problem. See what I supposed to do over here, I must take double transpose. First I must take transpose, and whatever transpose matrix you have, of that you have to take another transpose, and you have to check whether you are getting your matrix A back or not. Okay. Same way you have to do this as well as this. Okay. Fine. So let's proceed further. Practice problems. So here see, A, B and C you have, again you need to verify these all 5 properties. By the way, all these 5 properties are very important for science students as well as for commerce students. You may get these kind of problems for the exam. Now look at this second problem over here. What is given? A is this square matrix of order 3. You have B here, that is a column matrix. Here you need to show that B dash in B transpose into A into B is null matrix. So show that it is null matrix, in the sense when you multiply these 3, the answer is supposed to be a matrix with all entries as 0. Let us talk about next, symmetric and skew symmetric matrix. Again this is very important concept, symmetric and skew symmetric matrix. Okay. So over here, what do you understand by symmetric matrix? A symmetric matrix, here see, is always square matrix. Remember, a square matrix is called symmetric if here see, Aij is equal to Aji for all I comma j. What does it mean? The transpose of the matrix is equal to your original matrix A. Okay, you can see here A transpose equal to A. Simple definition. If A transpose is equal to A, what you can say? The given matrix is symmetric matrix. So what do you mean by skew symmetric matrix here? If A transpose is the negative of your original matrix, then it is skew symmetric matrix. Look at this here. A square matrix is called skew symmetric matrix if Aij is equal to minus of Aji for all I comma j. So you need to just remember these two things. A symmetric matrix is a matrix which satisfies this condition. The transpose is equal to the original matrix. And skew symmetric matrix satisfies this condition, that is your A transpose is the negative of your original matrix. Okay. Now over here see, I gave you all standard form of symmetric matrix. This is very important. Now over here see, when you talk about standard form, look at the pattern of this matrix, and I said this has to be square matrix. Okay. So here see, I considered matrix of order 3. So along the diagonal you have A, B, C. 3 different numbers. Perfect. Now look at this now. This is equal to this. So these two entries supposed to be same. I mean to say A21 supposed to be equal to A12. See, I marked it with blue color. Okay. Now this A3, here see, A31 has to be equal to your A13. Look at this green color which I had marked over here. So these two entries supposed to be same. Then you have F and F. Look at this. This is here, see, this is your A23. A23 supposed to be equal to A32. Look at this. Okay. And if you get this kind of pattern in the matrix from direct observation, you can say the given matrix is symmetric matrix. You don't have to take transpose also. Okay? Now, look at the square matrix of order 2. It is very simple. See, you have A, you know, I can have same number also, I can have different number also, but here see, along with the minor diagonal, see, this is your principal diagonal, this is your minor diagonal. Along with the minor diagonal, both the entries has to be same. Okay, so if you have this pattern in the square matrix of order 2, by direct observation you can say the given matrix is symmetric matrix. Now here, look at the standard form of skew symmetric matrix. Look at it. See, along with the principal diagonal, all the elements are 0. This is very, very important. What I said, along the principal diagonal, all the elements are 0. See. Okay, which I marked in red color. Okay, and here see these two entries, see. One is the negative of the another. Look at this, H minus H. Here it was H, same, but here it is what? H minus H. Here it's G, so here it is minus G. Suppose here it is G, then here it will be minus G. So whatever entry you have, the negative of the entry will come over here. Next here. This is F, so this is minus F. Not necessary on the upper half you will have all negative and in the lower half you will have positive. It is not necessary. Just remember whatever entry you have, the negative of the entry is supposed to be over here. Okay, so if you see this kind of pattern in any matrix, you can say by direct observation the given matrix is skew symmetric matrix. So here in case of 2 by 2 matrix also the similar pattern continues. You can see along with the principal diagonal what you have 0, 0, and along with the minor diagonal what you have the negative of the first entry. Okay, so this is how you understand symmetric and skew symmetric matrix. Now certain theorems you people need to know here. If A and B are symmetric matrices, then A plus B is also symmetric matrix. So if A and B both are symmetric matrices, then A plus B, the product what you get, A plus B is also symmetric matrix. Second one, sum of two skew symmetric matrices is also skew symmetric. The sum of two skew symmetric matrices is also skew symmetric. Third one, if matrix A is symmetric as well as skew symmetric, then A is 0 matrix. Okay, so again this is very important. So if I would say here, if I would say given matrix satisfies both this pattern, then I would say the given matrix is 0 matrix. Okay, so now the fifth theorem is very, very important. You may get problems also based on it. So over here, before I go to fifth, I must talk about fourth because it is continuation of, here see, the fifth is continuation of fourth. So for any square matrix A with real number entries, A plus B transpose is a symmetric matrix and A minus A transpose is skew symmetric matrix. Okay, so A plus A transpose is symmetric and A minus A transpose is skew symmetric matrix. Okay, so this is very, very important, and based on these two assertion, I would say we construct fifth theorem, that is any square matrix can be expressed as sum of symmetric and skew symmetric matrix. So over here see, basically this sentence, this statement means this. Here A equal to half times A plus A dash, plus half times a minus a dash. Now you people will say why this half is multiplied over here. See, my final output supposed to be a. So if I don't multiply this half over here, I won't get a back. I will get 2a. Okay, so that's why this half is very necessary over here. Okay, so this statement becomes very important. Now what kind of problems you will have on this theorem? Here see, the problem is here. Express the matrix A as sum of symmetric and skew symmetric matrix. Now here see when you get this kind of statement, what you need to prove? You need to prove this statement. You can see this is your LHS, this is your RHS. Okay, now look at the steps, what to do. Now you need to first find, here see, half times a plus a dash. How I will proceed? You know how to add two matrices. So I will say a plus the transpose of the original matrix. Whatever matrix I get, to that I will multiply half. I will get one matrix. When I talk about second step, similar way I have to do, but I have to go for a minus a dash. Here I need to add, here I need to subtract. And then I have to multiply the constant half. So I get step 2. When I go for the step 3, what I need to do? See, I need to get my RHS. To get my RHS, what is given? Step 1 plus step 2. So what matrix I get over here? Plus I will add this matrix. So I will get here RHS I will get, and which is equal to your given matrix A. Perfect? So this is how you get problems based on this fifth theorem, which is very important. You can solve as many problems you can get from different reference books. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.